Good evening. The fantastic Akiva Solemani.
Hello everyone, my name's Akiva. I'm retired now. I was a maths teacher for 40 years. I taught in secondary schools, further education colleges and universities. Now often when I inform people that I'm a maths teacher, quite often the result is, maths, oh no, I was always hopeless at maths, which makes me very sad. But what does get up my nose a bit is when some people sort of boast of it. They say, oh, I was always hopeless at maths. I was much more on the creative, artistic side. So I think it's a dreadful attitude. It's like, you know, it's great to be bad at maths because it proves you're artistic and creative, which is a dreadful attitude, especially if it rubs off on young people. But anyway, I do understand that a lot of people do have difficulties with maths. As I say, I've taught maths to adults in FE colleges, and I notice a lot that when I start teaching a bit of maths, this sort of glazed look comes over their eyes, and you know, this mental block comes down, and I have to work very hard to get them to relax, to not be afraid, and to convince them that they're perfectly intelligent people with no neurological condition, and there's no reason why they shouldn't be perfectly capable of understanding a bit of maths if it's taught to them properly. So anyway, as you can imagine, as you can guess, I love maths, but to me it's the most beautifully aesthetic subject, and I'm particularly interested in the history and philosophy of maths, and I'm particularly interested in this guy, Euclid. Now, he was an ancient Greek mathematician. We don't know his exact dates, but we know that he flourished around 300 BC in Alexandria, nearly 2,500 years ago. Now, what he did, he achieved this monumental piece of work. He collected together all the maths that was known in his time, which was geometry and arithmetic, not algebra. That wasn't invented till about 1,000 years later by Arabic civilizations. He collected together all the maths that was known at his time, and he proved them all. He proved just using 5 very, very simple axioms, things that are so obvious that you don't need to prove it. Because if you're going to prove things, you have to start off with something that you don't need to prove, otherwise you never start. So he started with 5 very simple axioms, and he proved, without any shadow of doubt, all the maths, all the geometry that was known in his time. He wrote this book called The Elements, this work called The Elements. It contained 13 books which proved 465 propositions in geometry, 465. Now once, he called them propositions to start with. Once he proved it, then you're entitled to call it a theorem. A theorem is different from a theory. A theory, you just can keep confirming it or disprove it. You can never prove it absolutely. But with a theorem, it's definitely true. You know it's absolutely true, but it's proved logically. Now, for example, the 47th theorem it proved was Pythagoras' theorem. Do you remember Pythagoras' theorem from school? If you have a right-angled triangle with a straight corner, and you draw squares on each side, the biggest square is equal to the other 2 squares. So the area of the red square is equal to the other 2 areas added up. Now he started off with 23 definitions. Definition of what is a point, what is a line, what is a triangle, what is a circle, etc., etc. And then he wrote 5 what he called common notions, which are sort of like axioms, but not applicable just to maths. They're applicable generally. Right? And these 5 common notions were: things which are equal to the same thing are equal to each other. I don't know if you've seen the film Lincoln, with Daniel Day-Lewis playing Abraham Lincoln. He quotes this line in his argument for abolition of slavery. Things which equal to the same thing equal to each other. For example, if if I've got the same amount of money as Chadham and Dan,
0.
and Tim's got the same amount of money as Chadham and Dan, then Tim and I must have the same amount of money. Must do. If equals be added to equals, the wholes are equal. So if Tim and I got an equal amount of money, and Chadham and Dan gives us both £5 each, an equal amount, we're still equal. Tim and I are still equal. If equals be subtracted from equals, the remainders are equal. So Tim and I are equal, Chadham and Dan takes away £2 from us each, we're still equal. Tim and I are still equal. Things which coincide with one another are equal to one another. So, like if one triangle fits exactly onto another triangle, well, they're the same triangle, must be. And the whole is greater than the part. Obviously, the whole cake is bigger than a slice of the cake. So these are obvious, simple truths. Right. Now, he also stated 5 postulates or axioms which related specifically to geometry. Now, an axiom, what is an axiom? It's a truth. It's so obviously true, so simple, so self-evident, it doesn't need to be proved. Now, I can't over-exaggerate the importance and the influence that Euclid's work had. It was held up as the most perfect piece of work possible. You start off with some truths that are so obvious that nobody can deny them, and then you prove logically, absolutely, everything that comes afterwards. So it's a perfect piece of work. And this had a huge influence across all cultures. For example, the philosopher Baruch Spinoza, he wrote a book called Ethics, but its full title was Ethics Proved in Geometrical Order. Now, it was nothing to do with geometry, but he specifically used Euclid's method. Started off with some axioms that are obviously true about ethics, and then tried to deduce what comes afterwards. Another example of Euclid's influence. Look at this. We hold these truths to be self-evident, that all men are created equal, that they are endowed by a creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. This is from the American Declaration of Independence. We hold these truths to be self-evident. The founding fathers were specifically, deliberately following Euclid's method, starting off with some truths that you have to accept as obviously true. So, what were his 5 axioms? Right, the first one, to draw a line from any point to any point. What does that mean? If you've got 2 points, you can draw a line between them. Obviously true. Second one, to produce a line continuously. So if you've got a line, you can make it longer. Can't deny that. To construct a circle with any centre and radius. So if you're given a centre and length of radius, then you know how to draw that circle. That all right angles are equal to one another. Well, this is hardly worth saying, it's so obvious. One right angle, another right angle is the same, because they're both right angles. Okay, now, what comes next? Don't run screaming out of the auditorium when you see this. Right, this is what caused all the trouble. Euclid's 5th axiom. That if a line falling on 2 lines makes the interior angles on the same side together less than 2 right angles, the 2 lines, if produced indefinitely, meet on that side on which are the angles together less than 2 right angles. Now, what do you think to that?
It's not his best work.
Your reaction is probably the same as mine when I first. What the fuck is that? Right. So, people were unhappy with this as an axiom, because an axiom is a truth that's so obviously true, so simple, so evident, doesn't need to be. Well, that's not simple. It's not so. You don't even know what it's talking about. So mathematicians were very unhappy with that axiom, right? And they tried various ways for it not to be an axiom. I thought first, well, maybe if we could do without it, we could still prove everything that he proved, but without that, they found they couldn't. They had to have that. Another way they tried to do it was to see if they could prove that axiom from the other four axioms. So it wouldn't need to be called an axiom if you could prove it. But they found they couldn't do that. So then they tried to use a method called reductio ad absurdum, which I'll come to in a minute. But what is that axiom actually saying? It's saying if you've got two lines, and you've got a line going across them, it would make angles. And they're saying that if you draw the black lines longer, they will meet on the side of the red angles. They won't meet on the side of the green angles. Which makes sense. Right? They'll meet there. So, that is equivalent to this. If the red angles and the green angles are the same, they're all right angles, they won't meet above the line and they won't meet below the line, will they? Right? So, they tried to prove this axiom by a method called reductio ad absurdum, which means if you want to prove something, assume it's not true, see that that produces a contradiction, and that way you proved what you wanted to prove. Right? So again, if you want to prove something's true, assume it's not true, show that that assumption leads to a contradiction, so everything must be true. I want to give you an example. Right, this is a reduction to absurdity. I want to give you an example of reductio ad absurdum proof using prime numbers. Remember what prime numbers are? A prime number can only be divided exactly by one in itself. So for example, prime numbers 2, 3, 5, 7, not 9, that could be 3 times 3. 11, 13, not 15, that would be 3 times 5. 17, 19, not 21, that would be 3 times 7. 23, not 25, because that would be 5 times 5. Not 27, that's 3 times 9. 29, etc., etc., etc. Right? Now, prime numbers, the further up you go into the millions and billions and trillions, prime numbers become very rare. You can go for millions and millions without finding another prime number. So people wondered, could you get to a prime number that is so big that you can't get another prime number afterwards? That is the last final prime number. So this proof, to prove by reductio ad absurdum that prime numbers go on forever, that there isn't a biggest prime number. Now we can prove this by reductio ad absurdum. So how do you do this? If you want to prove that there isn't a biggest one, you assume the opposite. You assume that there is a biggest prime number. Right? So we assume there is a biggest prime number, there isn't a big one after it, call this number p. So if p is the last prime number, we can theoretically construct a new number. You multiply all the prime numbers that there are, all of them up to and including p. So we've got all these prime numbers, 2 times 3 times 5, etc., dot, 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 times p, the final one. Right? Now, see what happens if we add 1 to this new number. You've got all those numbers multiplied together, plus 1. And look at this new number. 2 goes into it, times all the others, remainder 1. 3 goes into it, times all the others, remainder 1. All of them go into it, times all the others, remainder 1. In other words, nothing goes into it, exactly. So this must be a prime number, which is obviously bigger than p. So we've reached a contradiction. If p is the biggest, p is not the biggest, which can't be true. So we've proved what we wanted to prove, that there isn't a final one. Final one's gone forever. So they wanted to use this method to prove this. Right? So saying, right, we want to prove that this is true. So to assume the opposite, assume it's not true, what does that mean? That means that they can meet. Right? Now, they thought this would lead to a contradiction, but they found that it didn't. It didn't reach a contradiction. How do they know they didn't? Maybe they didn't try hard enough. It doesn't lead to a contradiction because they use what's called mathematical modelling. They make a model of it, which is this. If two people are standing at the equator and they walk northwards, they're starting off at right angles, but they meet at the North Pole. Now this looks like it's cheating, but it's not. Just you have to give a bit of a tweak to the definition of a line. So first of all, when they came up with this, it was only like about 200 years ago. There were two different mathematicians brought this up, and at the time they thought, "Oh my God, what have we done? We can't go against the great Euclid. This is sacrilege." Other mathematicians will laugh at us, but they were right. It doesn't lead to a contradiction, and it led to a whole new series of what the foundations of maths were. Like if you start with any set of axioms, you can deduce whole new systems of mathematics. So this isn't to say that Euclid was wrong. Euclid was still perfectly right. He's still sort of revered, but it just opened up a whole new world of different systems of mathematics. It freed mathematicians from the shackles of Euclid, and it opened up whole new theories of what the foundations of maths were. Anyway, that's it. I hope you found it a little bit interesting.